Previously, we asked the following question. Given the field in one plane, how does the field propagate to another plane? To answer that question, we introduced the angular spectrum method. Now, we will ask the same question, but we will answer it by introducing a different approach. With this approach, we can use wave optics to describe the imaging process that we previously described using geometrical optics. In doing so, we gain understanding about how the wave nature of light affects the image quality. This approach is based on Huygens' principle, which will lead to a diffraction integral called the Rayleigh-Sommerfeld integral. We can apply approximations to this integral to obtain the very useful and widely used Fresnel and Fraunhofer diffraction integrals. With these tools, we can then analyze a simple imaging system and see how the image formation is affected by the wave nature of light. So let's start with Huygens' principle. Huygens' principle states that if you have a field, then each point acts as a source of spherical waves. To illustrate this principle in 2 dimensions, one can imagine putting a narrow slit in a water tank and sending a plane wave through it. What we see emerge on the other side is a spherical wave pattern. How can we describe this wave mathematically? A field with spherical wavefronts can be described by cosine kr minus omega t, where k is the wave number 2 pi over lambda, r is the distance from the point source to the observation point, omega is the angular frequency, and t is the time. However, when we increase the contrast of the image, we see that the amplitude of the wave decreases with distance, so we include another factor 1 over r. Moreover, we see that the wave propagates more to the front, so in the z direction, and less to the sides, so in the x direction. We can describe this effect by including a factor cosine theta, where theta denotes the angle between the z-axis and the line connecting the point source and the observation point. This cosine theta can be rewritten more conveniently as z over r. Using complex notation, we can now write the impulse response as z over r squared times e to the power I k r. With this result, we can now construct the Rayleigh-Sommerfeld integral, which basically adds the contributions from all point sources in one plane to find the field in another plane that is separated by a distance z. So let's use x' to denote the 2-dimensional position vector in the source plane, and let x denote the 2-dimensional position vector in the observation plane. The distance between them is given by r, which we can calculate using Pythagoras' theorem. To find the total field at the observation point x in the plane z, we simply integrate over all the point sources in the source plane z is equal to 0. It turns out that if one were to derive this equation more rigorously from the wave equation, there would be a prefactor of 1 over I lambda. But for time harmonic fields, this factor is usually of little interest. Using this Rayleigh-Sommerfeld integral as our starting point, we can apply the Fresnel and Fraunhofer approximations, which are important and very commonly used. In these approximations, it is our aim to simplify the diffraction integral under the assumption that the propagation distance is large. In particular, we must simplify the expression for r. So how do we do this? Notice that r occurs twice in the integral, once in the denominator, once in the complex exponential. In the denominator, we simply approximate r with z if z squared is much larger than x minus x prime squared plus y minus y prime squared. However, in the exponent we cannot simply approximate r with z. Why not? The reason is that if we introduce a small error in r, say an error of lambda over 2, then the value of 1 over r squared doesn't change by much if r is much larger than the error we add to it. However, if we add the same error to r, then the complex exponential will change sign, regardless of how large r is compared to the error lambda over 2. Therefore, we have to be much more careful when approximating r in the complex exponential. So let's see how we can expand r more carefully. First, let's pull z outside of the square root. What's left under the square root is 1 plus something very small, because we assume that z squared is much larger than x minus x prime squared plus y minus y prime squared. We can approximate this expression using a first-order Taylor expansion, which will give us the Fresnel approximation. We can make one further approximation by expanding the squares and neglecting x prime squared plus y prime squared, which gives us the Fraunhofer approximation, which can also be called the far-field approximation. Now let's try to write the Fresnel and Fraunhofer diffraction integrals in a more comprehensible form. So we start with the expression for r in the Fresnel approximation. We can expand this expression, which will give us 4 terms. The first two terms don't depend on the integration variable, so they can be put outside of the integral. Then there are two other terms which do depend on the integration variable. The first one gives a quadratic phase vector, and the second one will give a complex exponential which is reminiscent of the complex exponential that is used in a Fourier transform. However, to obtain a Fourier integral there should be a 2 pi in the exponent, so using the fact that k is equal to 2 pi over lambda, we can rewrite the expression so that it becomes a Fourier integral. And finally, we obtain our result for the Fresnel diffraction integral. If we want to propagate a field from the plane z is equal to 0 to some other plane which is a sufficiently large distance z away, then we multiply the field with a quadratic phase vector depending on z, we Fourier transform the product, and we evaluate it in the spatial frequencies x over lambda z, y over lambda z. The resulting field is then multiplied by another quadratic phase vector. So to give an overview of the diffraction integrals, the Rayleigh-Sommerfeld integral is the most accurate of the ones that we'll discuss here, and it works by considering each point in the field as a source of spherical waves, and all the spherical waves are added together to find the propagated field. The Fresnel diffraction integral is an approximate integral that works for large propagation distances z, and it works by multiplying the field with a quadratic phase vector and Fourier transforming it. If the propagation distance z is even larger, then the quadratic phase vector can be neglected, and the propagated field is simply the Fourier transform of the initial field. When this approximation is valid, we say we're in the far field. We've seen that the Fresnel and Fraunhofer approximations are valid for large enough propagation distances z, but how large is large enough? When are the approximations we make valid? Let's look at the expression for r in the Fresnel approximation. For the sake of notation, we introduce the variable rho. Recall that we arrived at this expression for r by Taylor expanding r to the first order. The error we make in this approximation will be of the order of the next term in the Taylor expansion. So the error we make in kr will be of the order of 2 pi over lambda times 1/8 times rho to the fourth over c to the third. So when is this error acceptable? Since we're looking at a complex exponential, which is periodic with period 2 pi, we require that the error must be much smaller than 2 pi. If we then solve for z, we find that z over lambda must be much larger than 1/2 times rho over lambda to the power 4/3 in order for the Fresnel approximation to be valid. Now let's look at the Fraunhofer approximation. The term we neglected there was the quadratic phase vector x prime squared plus y prime squared over 2z, so we have to see how large the propagation distance z should be in order for this term to be negligible. Let's assume that the initial field is restricted by an aperture with radius r, so x prime squared plus y prime squared is smaller than r squared. Again, we want the error in kr to be much less than 2 pi, so we find that 2 pi over lambda times r squared over 2z should be less than 2 pi. Solving for z then gives that z should be much larger than r squared over 2 lambda in order for the Fraunhofer approximation to be valid. We can divide both sides by z to find a dimensionless quantity called the Fresnel number that indicates whether the Fraunhofer approximation is valid or not. If the Fresnel number is much smaller than 1, we're in the Fraunhofer or far field region, and otherwise we're in the near field. Now that we know that a field can be seen as a collection of point sources and that we can make the Fresnel approximation, we can look at how we can use wave optics to describe how a lens forms an image. To start with, we will rederive some results we already know from ray optics to get some confidence in our model. Let's recall how imaging works in ray optics. We said that each point of an object emits rays in all directions, and an image is formed when the rays that come from the same point end up in the same point. What we've seen now is that each point of an object emits a spherical wave, and so in order to form an image, each spherical wave should converge in a single point again. From this we can infer two things. The first thing is about what rays actually are. They correspond to the direction that is perpendicular to the local wavefront. The second thing is about what a lens does. We see that the lens bends the shape of the wavefronts, and since the wavefronts describe planes of constant phase, the lens basically changes the phase of the field. So let's see how a lens changes the phase of a field precisely. We know that rays parallel to the optical axis converge in the back focal point. So in terms of waves, this means that a plane wave propagating along the optical axis is converted into a spherical wave that converges in the back focal point. A plane wave propagating in the positive z direction is described by e to the power ikz. A spherical wave converging in the back focal point 00f is described by e to the power minus ikr, where r is the distance to the focal point. We know from the Fresnel approximation that this spherical wave can be approximated by a quadratic phase factor. So somehow, in the lens plane z is equal to 0, the lens converts the flat wavefront into a quadratic wavefront. If we write down the equation for what happens at z is equal to 0, we find that if a field propagates through the lens, it gets multiplied by a quadratic phase factor whose strength depends on the focal distance. With this result, let's see whether we can derive the imaging condition for this lens. Suppose we have an on-axis point source located at 00, that we want to image. What will the location of the image Zi be? We know that we can describe the field emitted by the point source as a quadratic phase function. We know that at the lens plane z is equal to 0 it will be multiplied by another quadratic phase, and we know that after the lens there should be a converging field with a quadratic phase. This field can have a global constant phase factor theta that doesn't affect how the wave propagates. We can look at what happens at the lens plane z is equal to 0, which gives us an equation saying that 1 divided by the object distance minus 1 divided by the focal length gives minus 1 divided by the image distance. Rearranging this gives us the thin lens equation that we know from geometrical optics. Now let's see whether we can find the magnification of this imaging system. Again, we consider a point source, but this time it's an off-axis point source located at xo0zo that gets imaged at the point xi0zi. Again, we can write the spherical waves at both sides of the lens in the Fresnel approximation, and we know that at the lens plane z is equal to 0, the input field gets multiplied by a quadratic phase factor, so we can write down the equations for z is equal to 0. We can rearrange the terms of this equation and cancel out the 2's in the denominators, and then we can use the thin lens equation to rewrite the right-hand side. Then we can cancel out all the y-coordinates so that only the x-coordinates remain. Next, we expand the squares, and then we can cancel the terms with x squared on both sides. What remains are 4 terms. 2 of these terms don't depend on x, meaning that they don't vary with position, so they represent a global constant phase factor which is irrelevant for the propagation of the field. Cancelling out these terms, only 2 terms remain, which we can rearrange to obtain the formula for magnification that we also obtained using ray optics. So we've used wave optics to rederive results from ray optics, which gives us some confidence in the model we use. However, one may hope that by introducing a new, more complicated model, we will be able to derive new results that were beyond the reach of the simpler ray model of light. This is what we'll do next when discussing the point spread function, or PSF for short. So far, we've modeled the effects of a thin lens as a multiplication with a quadratic phase factor. However, the function with which the field is multiplied may be more complicated than that. In particular, the lens has a finite size, so the part of the incident field that falls outside of the lens gets multiplied by 0. This extra multiplication can be put in a function p of xy, which we call the Pupil function. If it only takes into account the finite size of the lens, it will be a step function that is 1 inside the lens and 0 outside the lens. But p can also contain additional information. For example, if there are aberrations in the lens, they may also be modeled in the Pupil function. Or sometimes we deliberately make p a complicated function to shape the focal field in a particular way, one example of which is apodization. But for the time being, let's just imagine p as a step function to take into account the finite size of the lens. So let's see what happens to the image formation if we take p into account. The field at the lens plane can be found by multiplying the incident field at z is equal to 0 with the transmission function of the lens. Then, we can propagate this field to the image plane z is equal to zi using the Fresnel diffraction integral, which means that we multiply the field that is transmitted by the lens with the quadratic phase factor, we Fourier transform the product, and we multiply the result with another quadratic phase factor. We can expand the exponent of the source term and collect the exponents containing the factor x squared plus y squared over 2. This will give an exponent containing the factor 1 over ZO plus 1 over ZI minus 1 over F, and because we've chosen ZI so that it corresponds to the image distance, this factor vanishes due to the thin lens equation. What's left in the Fourier integral is the Pupil function multiplied by a linear phase function. In it, we can write k is equal to 2 pi over lambda, so that the phase term looks more like the complex exponential in a Fourier integral. And from this, we can see that multiplying the Pupil with the linear phase function means shifting the Fourier transform of the Pupil function. We can rewrite the argument of the Fourier transform so that it has a common denominator lambda zi, and we can simplify the expression by introducing the following definitions. We define the point spread function, or PSF, to be the image that is produced by an on-axis point source, and this image is given by the Fourier transform of the Pupil function. We define M to be the magnification of the image, which is minus the image distance divided by the object distance, just like in geometric optics. So we see that the image produced by an off-axis point source is the point spread function that is shifted by an amount that depends on the location of the point source and the magnification of the image. Also, it is multiplied by a quadratic phase factor and a global phase factor that depends on the location of the point source. So how will these findings affect the imaging resolution? We've already seen from the angular spectrum method that the resolution is limited to lambda over 2 because when a field propagates, the evanescent field that contains the high resolution information decays exponentially. Now we'll see that the point spread function also limits the resolution. After all, in the case of ideal imaging, each object point should map to a single image point, but now we see that each object point maps to a PSF, which is not a single point, but rather, as the name says, a spread out function. The more spread out the PSF is, the lower the resolution. So can we say something quantitative about how spread out the PSF is? Let's assume an imaging setup in which there is no magnification, which means that the image distance is the same as the object distance, which is twice the focal length of the lens. Since the image is the same size as the object, the size of the point spread function is a direct measure of the resolution with which we can image the object. Because the PSF is given by the Fourier transform of the Pupil function of the lens, we find that if the lens is larger, the PSF becomes smaller, and vice versa. Also, we can see from the expression of the PSF that its size scales with lambda f. Therefore, one can estimate that the size of the PSF is proportional to lambda f over r, where r is the radius of the lens. So this means that light with a longer wavelength creates a larger PSF. Also, the ratio between the focal length and the radius of the lens determines the size of the PSF. For a microscope, the standard expression for resolution is given by lambda over 2Na, where Na stands for the numerical aperture of a lens, which is given by n sine theta, where n is the refractive index of the medium between the sample and the lens, and theta is half the angular aperture, and the angular aperture is the angular size of the lens aperture as seen from the focal point. Indeed, this quantity is closely related to the ratio r over f. Now let's see how we can describe an image of an object using the point spread function. We've seen that each point source creates a PSF in the image plane. If we consider an object O as a collection of point sources, then each object point will generate a shifted PSF. The total field in the image plane is then given by adding all those shifted PSFs together, which will give an image of the object that is slightly blurred, depending on the size of the PSF. However, it must be noted that even though we've been calculating fields so far, it is not the field that we see or measure. After all, the field, being complex valued, has an amplitude and a phase, but when we look at an image, we cannot see any phase information. We can only see bright and dark, which is described by the amplitude of the field. More precisely, what we see is the intensity of the field, which is given by the squared amplitude of the field. We must make a clear distinction between two ways an image can be formed, which are through coherent imaging or incoherent imaging. In the case of coherent imaging, the object is illuminated with coherent light, such as laser light. With coherent illumination, each point source in the object has a well-defined phase, which means that interference can occur between the PSFs in the image plane. This means that all the complex valued fields of the PSFs are added together, and we calculate the intensity of the total field. In the case of incoherent imaging, the object is illuminated with incoherent light, such as sunlight. Now, there is no fixed phase difference between different point sources of the object, so there cannot be any interference between the PSFs in the image plane. In this case, we must add the intensity of each PSF separately to find the total intensity. So let's see how the images are formed in these two cases. If we have a point source in the object plane, we'll see a PSF in the image plane. Another point source at another location will give another shifted PSF. If we have a line of point sources in the object plane, then we'll get a line of PSFs in the image plane, but depending on whether the PSFs add coherently or incoherently, the interference effects are more or less visible. Until now, we've plotted the square root of the intensity to make the details more clearly visible. But if we plot the actual intensities, the difference between coherent and incoherent imaging is still noticeable. We've just described how the image is formed by shifting and adding point spread functions, but there's another way to describe image formation which uses transfer functions. We obtain two expressions for the image formed in the coherent and incoherent case. One can recognize that these two expressions contain convolution integrals, and from Fourier analysis we know that a convolution in object space corresponds to a multiplication in Fourier space. So let's write these expressions for the image as a multiplication of Fourier transforms. In the coherent case, we multiply the inverse Fourier transform of a magnified object with a quadratic phase factor with the inverse Fourier transform of the PSF, and we know that the inverse Fourier transform of the PSF gives the pupil function of the lens. So actually what we're doing is the following. We're filtering out spatial frequencies of the object, just like in the angular spectrum method we were filtering out the higher spatial frequencies, and the smaller the lens is, the more spatial frequencies we're filtering out. This is consistent with our previous observation that when the lens gets smaller, the PSF gets bigger, and the image becomes more blurred. We can do the same thing for the case of incoherent imaging. In this case, we have to multiply the inverse Fourier transform of the intensity of the magnified object with the inverse Fourier transform of the intensity of the PSF. The inverse Fourier transform of the intensity of the PSF is given by the autocorrelation of the pupil function, which in this context is referred to as the optical transfer function, or OTF. So for incoherent imaging, the Fourier spectrum of the object intensity is modulated by the OTF. Finally, let's discuss a particular property of the lens, namely that it can perform a Fourier transform on a field. Let's consider an incident field u xy0 that goes through the lens and is multiplied by a quadratic phase factor. We can propagate the transmitted field to the backfocal plane using the Fresnel diffraction integral. This means that we multiply the transmitted field with a quadratic phase factor, Fourier transform the product, and multiply the result with another quadratic phase factor. We find that the quadratic phase factor of the lens is cancelled out by the quadratic phase factor of the Fresnel propagator, so the field at the focal plane is given by the Fourier transform of the incident field at the lens plane multiplied by a quadratic phase factor. It's interesting to note that this is similar to what happens with Fraunhofer or far-field propagation, so using a lens is a way to create a far-field pattern without requiring a large propagation distance. But what we're looking for right now is a pair of fields that are related to each other by Fourier transform without any additional quadratic phase factor. Let's consider the field in the front focal plane and see how it's related to the field at the lens plane. More specifically, we'd like to know how their Fourier transforms are related, so it's convenient to use the angular spectrum method. And the angular spectrum method tells us that the Fourier transforms of the two fields are related by a phase factor. Note that we evaluate the Fourier transforms in kx over 2π and ky over 2π, because the complex exponential in the Fourier transform by definition has a factor of 2π in it, so it has to be divided out. The phase factor that relates the angular spectra of the two fields can be approximated using the Fresnel approximation, yielding once more a quadratic phase factor. The expression we get has kx and ky as its variables, but we want to substitute a function that has spatial coordinates x and y as its variables. So we have to substitute kx by k times x over f and ky by k times y over f. Once we've done that, we can plug this result into the expression for the field at the backfocal plane, and we find that the two quadratic phase factors cancel each other out. And so we found our main result. The fields in the backfocal plane and front focal plane are related to each other by Fourier transform. This may be an interesting result by itself, But is it also in any way useful? One way in which it is useful is that it provides us physical access to the Fourier transform of a field, which means that we can apply Fourier filtering techniques. For example, consider this two-lens system where the lenses have equal focal lengths and are separated by twice the focal length, so that the back focal plane of the first lens coincides with the front focal plane of the second lens. The first lens generates the Fourier transform of the field in its front focal plane, and the second lens transforms it back to a mirrored version of the original field. Now what we can do is to insert an optical component in the Fourier plane to manipulate the Fourier transform of the field. For example, one could block the lower spatial frequencies to create a dark field image of the field, or one could phase shift the low spatial frequencies to create a phase contrast image of the field, which is useful for samples that are completely transparent and are therefore practically invisible in normal bright field images. It must be noted, however, that in actual dark field or phase contrast microscopes, a different configuration is used, though the general idea behind it is similar.